Parallel Programming Difficulties, The Three Challenges, by Don Vance Green at Salt Lake Community College, CSIS 2810. According to Wenmei Wu's PSI Chief Scientist research, as we seek to develop parallel applications, we must understand that such development presents at least three major challenges. The most difficult challenge is that some important problems do not have massively parallel algorithms that exhibit desired behavior. Secondly, challenges arise when programs that use parallel algorithms do not have enough data to achieve scalability in multi-core processors. Lastly, perhaps the least daunting of the three, is that for parallel algorithms with high levels of parallelism and significant data locality, engineering the implementations of parallel algorithms to achieve good scalability is still challenging. The most difficult challenge, as stated above, doesn't have large enough algorithms to achieve the behavior wanted. Exaflop's performance, for example, if you want to achieve in the near future, computer scientists have to develop a billion-way parallelism, which is only true if the clock frequency stays at the current trends. Diving even deeper, down to the chip level, developers will need to find an algorithm that will continue down the performance growth we've already discovered by using an at least 10,000-way parallelism. According to Wu, these algorithms fall short with these standards. For the exaflops example, the CDC Controlled Data Core developed the CDC 6600, their first supercomputer, operating at 3 megaflops. However, nowadays our supercomputers run at 1 billion times faster. But for someone to achieve an exaflop, you need to retrieve a quintillion operations a second. This chart describes the projections roughly needed from 2012 to reach an exaflop, which would be estimated to be around 2018. The number one computer since June 2013 is the Tianhe 2, a supercomputer developed by China's National University of Defense Technology. This computer runs at 33.86 petaflops. That's quadrillions of calculations per second. The first challenge, simply put, has three levels that need to be addressed. Firstly, there are some problems that are without a work-efficient algorithm to exhibit the massive parallelism. The computer industry doesn't know how to solve these problems without drastically increasing the complexity of computation. Delaney's triangle in mathematics is a set of points, P, inside of a plane, where there is not a single point inside the circumcircle, of any triangle, and maximize the minimum angle of the triangles, where skinny triangles are avoided. These are algorithms that can solve this problem in small amounts. But when it is being asked to solve for large-scale problems, we lack the methods to divide this into individual and independent parts. Finding parallel algorithms or methods that would correctly partition the functionality would greatly enhance the fundamentals of computer science. However, to have the expectations to find these methods rapidly in our current world is unrealistic. But to continue down this path to benefit the long term is excellent work in this area. Secondly, in the first challenge, there are parallel algorithms that work with parallelism, but the quandary arises on their stability. Parallel cyclic reduction, PCR, constantly splits down the problem to its basic components. PCR is not efficient to be working by itself, running at big O and log n. But combine it with Thomas algorithm, PCR becomes work efficient. Thomas algorithm, also known as the tri-diagonal matrix algorithm, TDMA. This is a form of Gaussian elimination used to solve systems of equations. Once these two algorithms are combined, there has been excellent scalability using large data amounts. However, even with the amount of research done with PCR, it has been found to be incredibly unstable with large numerical values. So due to this information, PCR algorithm has been dwindled down on its use. To achieve numerical stability regarding these parallel algorithms, further research and testing must be done. Level 3. There are applications that consist of parallel algorithms that have complications from the amount of load offsets, resulting from the non-uniform distribution of data. Breadth first search, BFS for example, is used for many graphing problems. This graphing search scales well for graphs, distributed evenly, where the nodes and their neighboring nodes doesn't have a huge difference. However, When the nodes begin no longer in uniform, the performance of the breadth-first search drops quickly. Regarding scale-free graphs, there results imbalance that cause parallel algorithms to run poorly, slower than algorithms that run sequentially. Many problems in the real world where graphs are a way to correctly solve them, skewed balances causing imbalance. This is an example of Facebook friends who has 10 million friends. Starting at one side, you notice that certain spots are more balanced than others, where some only have a specific amount of friends in a certain area. This next part is a protein-protein interaction network, where the protein in the very center has its direct connection to the rest. Notice how the farther out ones are farther than the middle, making them imbalanced as there is more on one side compared to the other. Due to this high level of imbalance, there aren't enough processing techniques that can solve these problems. Although there are some solutions that haven't been discovered yet, at least assumingly, that can potentially solve this problem. Out of the 3 complications, challenge 2 comes to light when applications that use parallel algorithms don't have enough data reuse that would achieve scalability on a multi-core processor. The sparse matrix vector multiplication, SMVM, and the kernel of conjugate gradient solvers, which is sparse matrices, derived from systems of partial differential equations, PDEs, is a great example regarding the second challenge. The SMVM has plenty of parallelism in its algorithm. However, since there isn't data reuse in its algorithm, it causes the working set to be extremely large, and it won't be allowed onto the on-chip memory. Due to this off-chip memory, bandwidth limits the performance and won't increase to use the resources from the on-chip execution. Regarding the conjugate gradient solver, there comes a potential solution. This solution would allow multiple steps from the SMVM, but it won't perform the calculation by the residual gradient. Techniques today have the ability to organize the computation of the SMVM, but it doesn't converge fast enough from the residual gradient, affecting the stability of the solver. Even though there isn't enough data locally regarding the cause of scalability, there should be an impact down the line. The cost of the moving data as computing systems move from generation to generation has caused developers to strategically organize how algorithms work in their programs. Algorithms which have high levels of parallelism and implementing those algorithms, even though they achieve scalability, is still challenging to devise. Parallel programmers have to find ways to organize data, memory allocation, temporary storage, while making ways to devise a way to have data reuse. While creating ways to have data reuse, the developer must also break things down into tasks that will allow threads to access certain bits of memory that are placed on the memory hierarchy, but are all located on different levels. While doing those things, each hardware platform requires something different, causing the algorithm to be changed, and the arguments/parameters have to be determined separately. If someone is trying to program on anything, GPU, MIC, or even a multi-core CPU, the items listed above are tedious and highly error-prone. Even though this challenge will always be there, even if someone recompiles those applications, it is said to be the least worrisome of the 3 challenges. Although these challenges have ways to be bypassed, they still pose problems in parallel programming. Wu states, problems with good solutions to these challenges enjoy excellent scalability and efficiency. Others struggle.